Welcome back, everybody. Let's finish up our discussion of probability. So far, we've talked about 3 different perspectives of probability, and I've taught you a 3-step method for computing basic probabilities. We talked about 3 different rules for computing probability, and those rules allowed us to compute more sophisticated probabilities. For example, the 3rd rule allowed us to compute joint probabilities, and we practiced doing that when we were using sampling with and without replacement. And finally, in this video, we're going to talk a little bit more about joint probabilities, and we're going to compare them with conditional probabilities. Remember, we're trying to learn some basics about probability so we can apply that information for when we do inferential statistics. As you know, joint probabilities are probabilities that look at the joint occurrence of 2 different events. For example, in that first table, we can compute the joint probability of a defendant being black and receiving the death sentence. And of course, we can then compare that joint probability with the joint probability of a defendant not being black but receiving the death sentence. In this table, the cell percentages, right here and right here, these cell percentages are the joint probabilities. So that you can take more time later to compare the joint probabilities and conditional probabilities, right next to where it says cell percentage over here, just put down JP so you remember that row lists joint probabilities. Conditional probabilities are a little bit different, and in this table, the conditional probabilities are the row percentages. So where it says row percentage, right after that, put a CP for conditional probability. In this situation, an example of a conditional probability would be the probability that a person receives the death sentence given that they're black. And then, of course, we can compare that probability with the probability that a person receives the death sentence given that they're not black. As you see, sometimes we're looking at some controversial topics, and because we can compute statistical analyses a variety of different ways, the overall story can get complex. So let's walk through a simpler example for today. We're going to be comparing people with children with people who have no children. And we'll be looking at if they wear their seatbelt or if they don't wear their seatbelt. Along the way, we'll compute a basic probability like we learned originally. Then we'll compute a few joint probabilities. And then finally, we'll compute a few conditional probabilities, just so you can see how they're all similar and how they're all a little bit different. Let me change the views and we'll work these out together. Let's look a little bit more closely at our data. We're essentially comparing 2 groups based on their parenthood status. Some people have children. There are 20 of those people. Some people have no children. There are 80 of those people. So there are 100 people altogether. In these tables, our sample size is always in that lower right-hand corner. We're looking to see if people wear their seatbelt. There are 30 of those people. And if people do not wear their seatbelt, there are 70 of those people. So again, 100 people altogether. Based on these frequencies, let's just compute a simple probability. What's the probability that someone in that sample of 100 people wears a seatbelt? Think back to the basic procedures that we discussed for computing a simple probability. The first thing we need to do is look and see how many people are actually wearing a seatbelt. In other words, what's the number of ways in which this event is occurring? There are 30 people who wear a seatbelt. So we've got 30 divided by the number of ways that this event can occur. Well, there are 100 people overall. 30 divided by 100, of course, equals 0.30. So the probability of randomly selecting somebody from those 100 people and finding that they wear a seatbelt is 0.30. So it happens about 30% of the time. You'll see in this next example, we're computing a joint probability. So I'm going to put down JP. We know it's a joint probability because I see the word and in there. I'm trying to figure out the probability that somebody has children and they wear a seatbelt. In the first row of the table, I see the people who have children. And then in this column right here, I see the people who wear a seatbelt. So the joint frequency right here represents the people who have children who wear a seatbelt. And there are 15 of those people. So we have 15 people who have children and wear a seatbelt out of 100 people overall. And that, of course, equals 0.15. So out of our entire sample, if we were to randomly select someone, about 15% of the time, we would find someone who has children and wears a seatbelt. Let's compute another joint probability. And again, I can tell right off the bat that it's a joint probability because I'm looking at the joint occurrence of these two events. So what's the probability that someone has no children and they do not wear a seatbelt? As we're looking at the table, it's this second row right here that shows the people with no children. And it's this column right here that shows people who do not wear a seatbelt. So the frequency that I'm interested in is right here, 65. There are 65 people in this sample who have no children and do not wear a seatbelt. So let's compute that joint probability. We've got 65 people out of 100. That equals 0.65. So if we were to randomly select someone from that sample of 100 people, about 65% of the time, we would select someone with no children who does not wear a seatbelt. This is where I think things get a little bit more interesting. We're going to compute now a pair of conditional probabilities, CP. They're called conditional probabilities because they're based on some condition being true. In this case, I'm trying to compute the probability that somebody wears a seatbelt given that they have children. Do you notice how I just stressed that a condition needs to be true? We're trying to figure out the probability that they wear a seatbelt given the condition that they have children. This symbol that you see right there is a pipe, and it should simply be read as the word given. So what's the probability that someone wears a seatbelt given that they have children? If this probability is just based on the people who have children, remember the people who have children are listed in this line right here. There are only 20 of these people. So when we compute this probability, it is just based on those 20 people. How many people actually wear a seatbelt out of those 20? 15. So for how many people does this occur? For 15 people out of how many? 20. 15 divided by 20 equals 0.75. So 75% of the people with children wear a seatbelt. Stated another way, of all of the parents who have children, if I were to randomly select one of them, 75% of the time I would find someone who wears a seatbelt. Let's compute another conditional probability, and you'll see it will be interesting to compare that first conditional probability with this second one. What I want to compute right now is the probability of somebody wearing a seatbelt given that they have no children. Do you see how this comparison is really going to be very straightforward? We're simply comparing the people with children to the people who do not have any children. So let's find where they are. In our table, it's this row right here that shows the people without any children. And we can see that there are 80 of those people. How many of them wear a seatbelt? 15. So based on those frequencies, how many people are wearing a seatbelt? 15. How many people are we looking at overall? We're only looking at people without any children. So in this case, there are 80. 15 divided by 80 equals 0.187. Let's just call that 0.19, or about 19%. So in this case, comparing these numbers, the story is really pretty clear. When we compare people with children and without children, people are much more likely to wear seatbelts when they have children. And that can be for a variety of reasons. When people have children, they're probably thinking in a more safety-conscious way. When people have children, they're trying to model good behaviors. There are a variety of reasons why we're probably finding this pattern of results. Okay, everybody, that wraps up our section on probability. As you know, we're going to be talking in probabilistic terms throughout the rest of the semester as we learn inferential statistics. And we're getting really close. We're getting very close to being able to compute our first inferential statistical test. And that test will be a z-test. We need to learn something else first, though. We need to learn about sampling distributions, and we'll do that in the next video. In the meantime, be safe.